All right, guys, continuing on through our Unit 6 here. As always, right, we'll start off with a little bit of review of last lesson and the bell work. So if you haven't already done that, then give it a pause and give it a try. If you have done it, then stay tuned and we'll take a look at it together right now. All right, so looking at that, if we take a look at this first one here, we know that the integral from 0 to 4 of fx dx is 5. And then we want to calculate the integral from negative 4 to 4 of fx dx. And we know that it's an even function. So because it's an even function, this means that this here can be written as 2 times the integral from 0 to 4 of fx dx, because we know it'll be the same on both sides of the y-axis. And so if we do that, we of course also know that this here is actually 5. So this is really just 2 times 5, or 10. So hopefully you remember that from last class. And let's go ahead and jump in here where we're going to take a look at the fundamental theorem of calculus in particle motion as well as average value. So there are 3 things that we want to keep in mind. And so, it's kind of awkward the way that that printed there. I'm not sure why velocity jumped way over here, but if we have the integral from a to b of vt dt, then that is equal to the position at b minus the position at a, where v of t represents the velocity and p of t represents the position. Okay? If we have the integral from a to b of v of t dt, then that is equal to the net distance the particle travels on the interval from t equals a to t equals b. And v of t has to be greater than 0 on the interval AB, that it also represents the total distance, okay? If it is not greater than 0 all the time, then that means that it will, or I guess technically it could also be always negative, then it will not represent the total distance. So then we get to part 3 here, where the total distance of the particle travels on the interval A to B, whether or not it is greater than 0 or less than 0. And so to be safe, we should probably always do this and just in case it changes directions, but that's why we've got the absolute value written on there. All right, so let's take a look at some examples practically here. So the velocity of a particle is moving along the x-axis given by the function v of t equals 3t squared plus 6, okay? We're going to try and do this without our calculator because we can. If the position of the particle at t equals 4 is 72, what is the position when t equals 2? So because we've got t4 and t2, that needs to be where we're doing our integral from. So we're going to integrate from 2 to 4 of v of t, which in our case, let's just write it out. So 3t squared plus 6 dt, okay? And we know that this is going to be equal to our position at 4 minus our position at 2. So now we can go ahead and work out what some of these things are. So this is the harder part over here. That's going to be t cubed over 3, and of course the 3's will cancel, plus 6t. And then technically plus c, I'm not going to bother writing plus c because we're going to be evaluating it from 4 to 2, which means that the c is going to cancel out anyway. And that's going to be equal to p of 4, which they told us is 72, minus p of 2, the thing we're looking for. All right, so here we can go ahead and plug this in. 4 cubed is going to be 64, plus 6 times 4 is 24, minus 2 cubed is 8, plus 2 times 6 is 12. All right, so that gives us 88 minus 20, and that's going to be equal to 72 minus p of 2 still. And then what I'm going to do is I'm going to take that 72, move it over, so I got everything all together on this side that isn't p of 2. So now I've got that this is equal to negative p of 2. And on this side, I'm going to have, let's see here, 68 negative 4. All right, and of course, if these are both negative, that would just mean that p of 2 is actually 4, because I can take everything and divide it by the negative 1. All right, so that allows us to find that position. Now, what is the total distance that the particle is going to travel in this time from 0 to 7? So now we're going to be integrating from 0 to 7. We're going to do the absolute value of the function from 3t squared plus 6 and dt, sorry. And then we're going to go ahead and do that. Again, we already know what it is. We just did it. So t cubed plus 6t, okay? And we're going to evaluate that from 7 to 0. So in this particular case here, that's going to give us 7 cubed plus 6 times 7 cubed, 343, plus 42. And so 385, and of course this is minus 0, because 0 times those stuff isn't going to matter. So the only thing that I'm going to clarify with this one, of course, is that we're talking about the total distance, so it should be the absolute value, which would mean that I would need to be careful if this thing ever changes direction, but it doesn't. 3t squared plus 6, it's impossible for me to make that thing equal to 0, because there's no way for me to make t squared a negative number, and so therefore I don't have to worry about it. Just to kind of show you what I'm talking about here, if I take that velocity 3t squared plus 6 and try to make it equal to 0, I'm going to end up with t squared equals, negative 6 over 3, so negative 2. And this is not possible. I can't ever make that happen. So that's why I don't have to worry about it, because this thing never changes direction. But I did take that into account, but I forgot to actually mention it the first time around. All right, so then let's keep going, and let's take a look at this new one. We're going to look at something that's got an exponential in it here, okay? Velocity of a particle that is moving along the x-axis is given by this function here. And if the position of the particle at t equals 1.5 is 2.551, what is the position when t equals 3.5? So obviously, if those are the two things that we're looking for, or am given, I have to integrate around those, right? I can't do it otherwise. And I need to integrate the velocity function. So that's that 0.5 e to the power of t times t minus 2 cubed. dt, and I should have brackets around that whole thing there. Okay, and we know that this is going to be equal to p of 3.5 minus p of 1.5. And when I do that, this is something I'm going to have to put on my calculator. It's hard for me to do that on the screen here, but if you're in class, I'll make sure I go through that. Otherwise, guys, what you're going to do is most likely, it depends on which calculator you're using, but you're going to go math, integrate, plug in this number and equation exactly as you see it here. If you change the variable to x instead of t, that might be easier for you. It depends on your calculator. The Inspire shouldn't matter which one. The TI-84s and 83s, they're probably going to be easier on t or on x. But that's what you're going to do. So I plugged that in already. And when I plugged that in, I got 15.919. Actually, I guess I could probably show you how to do it at least on Desmos. So give me a second to queue up Desmos. All right, so I got Desmos queued up here, so I can at least show you in here how we're going to do that. So you're going to, and it's basically the same thing on your calculator, just the buttons or the way you get there is a little different. But all right, so you're going to open up the Functions tab, or you might have to hit the Math button on your calculator. You're going to open up the integral, and I'm going to be doing this one from 1.5 to 3.5, and then I need to put in what my function was, which was 0.5 e to the power of x times x minus 2 cubed, and then I put dx here. And so if I do that, you can see I get that 15.919 like I was saying. So that's how I got that answer there, okay? All right, now let's go ahead and continue. I don't know why this is here. Let's move that out of the way. All right, so then let's continue. So the 3.5 is the one that I'm looking for, so p of 3.5 here. And the p of 1.5 was the one that was given to us, so minus 2.551. Obviously, I'm going to add that to the other side so that I can get my unknown by itself. And so I'm going to get here, I'm going to switch the sides, but p of 3.5 then is just going to be these two added together, which is what, 17, 470. There we go. 470. All right. What is the total distance that the object travels? So because it's a calculator question, I don't have to worry about trying to figure out where this thing is equal to 0. Instead, I can go ahead and just plug it into my calculator using the absolute value. So I'm going to go from 1 to 5, because that's the interval they've given us, of my 0.5 e to the power of t minus 2 cubed, and then d of t. And so what I'm going to do is put that into my calculator as well. So I'll show you how to do that here in Desmos. So it's basically going to be this same thing here, except I need to change this, the bounds here from 1 to 5. And the other thing I need to do here is this is not absolute valued currently. So I'm going to need to make sure that I take the absolute value of this function, which, sorry, it's right here. So there we go. So there's my absolute value, so I can put it in like that. And if you noticed, it changed. Let me actually just show that to you by putting it in here without the absolute value. And you see how it's slightly different. And that's because here at t equals 2, it's going to change directions. And that's why the absolute value one is bigger, because it's taking into account the total. This is our net distance. This is our total distance. So 9.13.067. So we got that 913.067 there. Awesome. All right, let's keep going here and try another one here. Graph of the velocity measured in feet per second of a particle moving along the x-axis is pictured below. The position p of t of the particle t equals 8 is 12. Use the graph v of t to answer the questions that follow. What is the position of the particle at t equals 3? So in order to figure that out, we've been given 8 and we want to find 3. So obviously that's going to be the bounds that we are integrating on. And we're going to do it for v of t dt. I'm not going to write the function because I don't want to take the time to figure out this huge function because it's a piecewise function. It's going to be annoying. And that's going to be equal to our position at 8 minus our position at 3. The position at 8 was, of course, given to us. It was 12 minus the position at 3. Actually, you know what? I'm going to move that over because I'm definitely going to need more room. So let's do this part first because that's going to definitely take some more work because I'm going to have to go over here. And if I'm going from 3 to 8, I've got to take this thing and split it up into a couple of different shapes here. So this one here is just a parallel or trapezoid, and this one's a triangle. So let's do this part in blue. And so the trapezoid there is going to be, let's call this side our base, so that those can be our heights. So that's going to be 5 times the average of our two heights, which is going to be 1 and 3. So 1 plus 3 here. And then I'm also going to need to add in this part here. However, let's do that in pink to kind of show that it's below, so it's actually going to be negative. So I'm going to be doing, instead of plus, really it's going to be minus, and that's 2 times 2 times 1/2. That's just a basic triangle, guys. And now that's equal to p of 8, which was 12, minus p of 3. All right, so I put all this together, I'm going to get 4 times 1/2 is 2, times 5 is 10. Minus, those ones are going to cancel, so minus 2 equals 12 minus p of 3. So I'll move over this 12 here. That's going to give me that negative 4 is equal to negative p of 3. And so, of course, that means p of 3 is going to be equal to 4, and that would be our answer there. All right, what is the acceleration when t equals 5? So let's think about that for a second. A of 5 is really the same as the v prime of 5. All right. So what I want to do is look at 5 here. This is the velocity. I want to find basically the slope of this. So the slope of that part of the line there. And it's down 5 over 2. So that's just negative 5 halves feet per second squared. All right. What is the total the net distance, the particle travels from 0 to 10? Okay, well, this is not quite as difficult as it looks because we have already found some of these areas. Because this area here will be identical to this one as well, which we had just found over here to be 10. And then this triangle down here, same thing. It's going to be same to the one that we already calculated, 2 times 2 times 1/2. So what we can do when we're putting all that together is instead of this being 10, it's going to be 20. I guess I should actually write it out. So the integral from 0 to 10 of v of d. Vt dt. And this case for us, it's going to be equal to 20 minus, this one was originally 2, so it'll be minus 4. And so we'll get that this is 16 feet. Awesome. Let's continue right along here with D and find the total distance that the particle travels from 0 to 10. So in this case, what we're going to do is instead of making that part that was below negative, we're just going to say it's still distance that we traveled. So we're going to make it positive. We're going to do the absolute value of it. And so that's going to be plus 4, meaning that we're going to go 24 feet. So total distance is 24, even though the net was only 16. All right, we love chart questions. Let's take a look at this chart question here. Table above shows values of a velocity in meters per second of a particle moving along the x-axis at selected values of time t. What does the value of the integral from 0 to 18 vt dt represent? I'm going to type this, I think, because I think it'll be a little bit easier here. And so this is really going to be the total distance. The particle moves from 0 to 18 seconds. Why is that? This is specifically because v of t is always positive, right? It's always the same sign. It's always moving in the same direction. So in that case, we can say, it's the total distance that this thing is actually moved. So now, using a left-hand Riemann sum of 6 subintervals of equal length, estimate this value. All right, so if we're using 6 intervals, I got 1, 2, 3, 4, 5, 6. So it's basically just going to be each column here like this. We've got 2 numbers together. And I think it's all uniform. Yeah, t is always going up by 3, so we're going to be able to use that. So what we can do is say that the integral from 0 to 18 of vt dt, we can estimate this using the Riemann sum, and it's going to be a width of 3 times all of our heights based on the left, because we're doing the left-hand Riemann sum. So that would be here, 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 and here. This one isn't included because that's the right side of the last one. All right, so that's going to be 2.3 plus 2.7 plus 2, technically 2.0, plus 1.3 plus 1.0 plus 1.7 plus 2, no, not plus 2.1, almost included that. All right, and that, if we put that into our calculator and simplify that, which I did here already, is 33 meters. So that's our estimation there. Now, what about if we do it with right-hand intervals? Well, it's exactly the same thing, except like it's still width of 3, but instead of including 2.3 here, if maybe I'll switch colors to kind of show you, we would end up using the right hand of each of those rectangles here. So instead of 2.3, we're going to include 2.1. But otherwise, it's going to be the same thing there. So the integral from 0 to 18 of v of d dt is going to end up being estimated as a width of 3 times, and this time, like I said, 2.7 plus 2 plus 1.3 plus 1 plus 1.7 plus the last one was 2.1. So it changes it ever so slightly, and this time we're going to get 32.4 meters. So you can see it's a little bit different. Last one we're going to do here is we're going to use the midpoint Riemann sum with only 3 intervals on it. All right, so if we've only got 3 intervals, actually maybe I'll do this in yet another color here. The 3 intervals means that I'm going to be using this interval, and this interval. So this time there's going to be a width of 6, and then it's midpoint, so that would be our midpoint there. That's the midpoint of the middle one, and that's the midpoint of the last one. So this is going to be the integral from 0 to 18 of v of d dt. And this time we're going to estimate it as a width of 6, and I can't remember what those were, 2.7, 1.3, 1.7. So 2.7 plus 1.7 plus, nope, that was the last one. What was the middle one? 1.3, there we go. All right, so plus 1.3, there we go. And when I put that all into my calculator there, I'm going to get 34.2 meters. All right, and so the last one we're going to do here is use trapezoids, which we know are usually more accurate for us, and we're going to do that from 0 to 18 with 6 subintervals. So, going to need a little bit of space for this one. We'll start a little bit further over. Our integral here is going to be equal to, we're still going to have our width of 3, but then remember there's a half because we're averaging all those heights. Now, I like to use a simplified formula here, so that means that we're going to use the first and last one, and then 2 times all the terms in the middle, which was 2.7 plus 2.0 plus 1.3 was the next one, plus 1.0 plus 1.7, because these ones are all going to be included twice because they are the left and right hand side of all of the trapezoids in the middle there. Then I'm going to take that, put that into my calculator, and see that I got 32.7 meters. Now we can make a pretty good estimate that that's probably a more accurate version of it. We could always take the integral and find out exactly and see. All right, find the average acceleration of the particle from 3 to 9. For what value of t in the table is the average acceleration approximately equal to v prime of t, or a of t, and explain your reason. All right, so our average acceleration here, that's where we would just find our v of 3 minus v of 9 over 3 minus 9, okay? If we do that, v of 3 and v of 9, v of 3 is 2.7 and 1.3. So 2.7 minus 1.3 over negative 6. That's going to give me, decimal. And if I put that in my calculator, I've got negative 0.233 meters per second squared. All right. Now, is this average acceleration approximately equal to v prime of t at some point? Well, in this case, really what that's asking us is, does MVT work? And so in this case, we can say that MVT guarantees a value exists between t equals 3 and t equals 9, such that v prime of t equals, I'm going to have to write that out, because I'm not going to be able to write that easily, such that it equals v of 3 minus v of 9 over 3 minus 9. Now, in our particular case here, I believe it ends up being 6 when I worked it out before. So it does actually exist, and we can, of course, now go and find it like we have in the past. All right, so our very last question here is going to be this one off of previous AP test from 2001. So a car is traveling in a straight road with a velocity of 55 feet per second at time t equals 0 and 0 to 18 seconds. The car's acceleration in feet per second squared is the piecewise linear function defined by the graph above. Is the velocity of the car increasing at t equals 2 seconds? Why or why not? So here at, sorry, which graph is this? A of t. Okay, this is the acceleration. Cars are straight with the velocity of this. The car's acceleration a of t in feet per second. Yeah, it's the piecewise function a of t. Okay. So in that case, if I'm looking for the car's velocity at t equals 2 seconds, then I need to understand what is happening there. So if I look up here, all right, so looking up here, we can see that our acceleration here is positive, and because that's positive, that means our velocity is going to be increasing at that point. So we can say, it's kind of awkward to write this one, but I got to move down here and we'll say yes, and our reasoning is really just because a of t is positive. And that means that it's going to be increasing or moving to the right, accelerating to the right, I guess is another way to think of that. All right, so then B, at what time interval from 0 to 18 other than t equals 0 is the velocity of the car 55 feet per second? So in this case, we know that from 0 to x, some value x, we don't know exactly what, of a of t dt, this will be equal to v of x minus v of 0. And the reason we're doing this is because at 0, where is it here? At 0, we know that it was 55 feet a second because it tells us that that's what it was at time 0. So doing this then, I can go ahead and start to work out what this might be. So this is going to be v of x minus 55. Now this part from 0 to x, if we're trying to make it so that v of x is also 55, that means that like this whole thing here needs to be 0, okay? Which means that that's our velocity is going to be the same there. Now, to look at that, in order to figure out where that's happening, what I want to do is look up here and determine where basically the area under the curve will be exactly the same, because I want this area above to be exactly the same as the area underneath, which will happen right there at 12. That's when I've got the exact same area. And if I do that, the reason I'm saying that is because that will make that integration 0, which means that I'm going to be back to my original speed of v of x, or v of x being 55. So what I can do is say, therefore, this is going to happen when t equals 12, and this is because I want that integration to be 0. So this would mean that the integration from 0 to 12 of a of t dt is going to be equal to 0. And you can see the picture up above where I kind of drew that to sort of show that, right? All right, so then next thing here is, see, actually someone's at my door, one sec. All right, sorry about that. Just had someone at the door I had to quickly go and talk to. So at the time interval from 0 to 18, what is the car's absolute maximum velocity in feet per second, and at what time does it occur? And then, of course, justify your answer, because it's calculus, right? So when are we going to know that this happens? Let's see. On the interval from 0 to 18, what is the car's absolute maximum velocity? So basically, we know that at this point, it's going to be back down to like nothing. Right? Like it's, or not back to nothing, back to the beginning. So 55. And then here, because we're accelerating the negative direction, we're going to be slowing down even further. So we're going to be less fast. So basically that means that it's either going to happen here at the very end or somewhere at the very beginning, right? So that we can kind of figure out what that would be. And so we need to kind of compare those. So the easiest way to kind of compare those is to notice that like this triangle here will be the same as, this triangle that's right there, meaning that at the very end, this extra part is going to make it slower. So it will be slower at this point. So we're going to be fastest then right here, because at this point, we've only been accelerating in the same direction. So it's not going to be any slower at all. So what we can do is say that this is going to happen at t equals 6. And then the rest of this is a bit of an explanation. So does it ask us what it is? What is the car's absolute maximum velocity? So we will need to. Actually, so let's go ahead and work that out first then maybe. So this is going to happen when we've got our integral. So we're going to have v of 6 is going to be equal to 55 plus the integral from 0 to 6. Why? Because we started at 0 at 55, and then v of 6 is that thing we're looking for at the end. I'm basically just rearranging the fundamental principle of calculus here. So just moving that around. And then this is, of course, a of t dt, because when I integrate that, I'm going to get the velocity, right? And so here, this is also like, you've probably seen this before, as accumulated change is the other way we often talk about this. Okay, so then I need to figure out what this is, and because in this case I don't actually have an equation, I just have this graph, I just need to work out what that parallelogram is, which I don't think we've actually done yet. So we're going to need to work that out. All right, so that's going to be 55 plus our total height was 15, or our base, times 1/2 times the average of the two lengths, which will be 2 plus 6. And so we're going to get, let's see, 8 plus 8, 4. So that'll be 55 plus that, which is going to be, that's 60. So that's, sorry, 115, not 105. So v of 6, therefore, is going to be 115. And what were we in here? Feet per second. So that will be the, that will be the absolute fastest velocity that we ever managed to reach. Because after that, we end up decelerating, essentially, because we're accelerating in the negative direction. And then while we do eventually accelerate in the positive direction again, it's not enough to counteract all that we decelerated. So it'll definitely be slower. All right. And then D. At what times in the interval from 0 to 18, if any, is the car's velocity equal to 0? And then justify our answer. So in this case, we already know that what happened at 12 was when we got back to our original, not back to 0, but back to 0, which was 55 feet per second. So essentially what we need to kind of set up then here for this one is to determine if anywhere from 12 to 18 will become negative 45. Now we know it should be like more negative because we already looked at the graph up here and we could see like this red portion is of course bigger than these, which cancel out. So it is going to slow us down. Is it enough to get us to 0 is sort of what we need to realize. Now the other way we could look at it is that of course the minimum speed we're going to go is at 16. And so we could figure it out that way as well. I don't think it matters which way you want to do this. So what I'm going to do is I'm going to set it up that way that I just said. So if the integral from 12 to 18 of at dt, okay, is basically ever negative 55 feet per second, then the car will be at velocity 0. Okay? I guess not we. I guess we should say the car. Then the car will be velocity 0. All right, so that means that all we need to do now is work out what that integral is there from 12 to 18. And so in this case, we're going to have that parallelogram and then this triangle. Because we know those two triangles cancel, we can really just find the area of this red part here. So if I find the area of that red part, that's going to give me the amount that it continues to slow us down. And that's going to be a width of 2 and a height of -15. So we've got that, basically that's actually going to be the integral from 12 to 14 of AT dt. And in this particular case here, this is going to be equal to, we just said it was 2 times -15. So that gives us -30. And so what that means is that that's not going to be enough to slow us down all the way to 0. And even if we tried to go, well, the slowest we could possibly go is, of course, at that 16. And so we found that integral from 12 to 16 of AT dt. Then we've just got that parallelogram. And so that parallelogram is going to be the width of -15 times 1/2 times the average of our two heights, which is 2 and 4. And so that's going to be 6/3. So that's going to give us -45 for that one, which is still not enough to get us all the way to that -55. So either way, we have determined that it's impossible for us to actually get all the way down to that -55. And so we can't ever be at 0. So our conclusion is that we can't actually get to 0, which I guess we should write. So therefore, cannot get to velocity equals 0 on our interval of like 0 to 18. So we probably could get there later in the future somehow if we slow down, but at least on what we've got, the data we have, it's never possible.